Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module production of ultra high vacuum, that is using thin film vacuum coating unit from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to learn about the thin film coating units. Secondly, we will learn the ultra high vacuum requirement in the growth of thin films. Then we will see the different types of deposition techniques of thin films. And in the end, we'll see the advantages and disadvantages of various deposition techniques. So to start with, let us have a brief introduction. What are thin films? Thin films are low dimensional materials. They are generally lying in the thickness range of few nanometers to several micrometers. The production of ultra high vacuum, that is ultra high vacuum means of the order of 10 to the power minus 6 torr, is an essential requirement for the production of high quality thin films. High quality thin films are the prerequisite for the manufacturing of many electronic and optical devices. There are several pumps available in the market to create the vacuum of desired amount. Generally, these pumps are categorized in two categories: 4 vacuum pumps and high vacuum pumps. The example of 4 vacuum pump is rotary pump, and that of high vacuum pumps are turbomolecular pump or TMP and diffusion pump. Now there are various techniques which we use using these pumps to produce ultra high vacuum in order to deposit high quality thin films. That shows the types of vacuum thin film coating units. These are the types of coating units in which a thin film is deposited inside a vacuum. So the first one is the pulse laser deposition technique. The second one is the thermal evaporation. The third one is the sputtering. The fourth one is the E-beam electron beam evaporation. Fifth one is molecular beam epitaxy. And the last one is PECVD or plasma enhanced chemical vapor deposition technique. Pulse laser deposition. Pulse laser deposition or PLD is a typical technique for the preparation of thin films of complex stoichiometry, well-controlled interfaces or multi-layer structures. In PLD, laser shots of the intense laser with specific wavelength and high energy are focused on the target of the material to be used for the deposition. The energy of the laser should be high enough so that it can ablate the target material. The deposition of the films can be performed under high vacuum conditions. The required vacuum is achieved with the aid of two pumps. The first one is a 4 vacuum pump, that is the rotary pump, required to create the base vacuum up to the order of 10 to the power minus 2 torr, followed by a high vacuum pump, that is turbomolecular pump, which can create vacuum up to the order of 10 to the power minus 6 torr. The full PLD process can be portrayed by 5 stages, which are as follows. The first stage is the light absorption in the solid. Second one is the one-dimensional plume expansion of the ablated material during laser irradiation. Third one is the free three-dimensional expansion into vacuum or a dilute background gas. Fourth one is the slowing down and stopping of the plume in the background gas. The fifth stage is the collection of ablated atoms on a substrate and subsequent film growth. The figure below shows the schematic of the PLD system. A high power ND-arc laser that is operating at the wavelength of 266 nanometer and having energy of 100 millijoules is shown. The deposition chamber is fitted with a turbomolecular pump which is of Pfeiffer company and creates a high vacuum of the order of 10 to the power minus 6 torr in the chamber. Also, the chamber is equipped with a rotating target carousel which can accommodate 6 1-inch diameter targets. This setup enables multi-layer deposition of different materials on the same substrate without breaking the vacuum. The substrate holder is available with PLD controlled heater assembly for substrate heating up. All 6 targets can be controlled externally via a microcontroller and can be programmed for the desired thickness of thin film by setting the number of laser shots and laser frequency. So you can see in the figure the target holder, laser input, substrate holder, target carousel control, vacuum display, gas flow controllers and the substrate temperature heater. Thermal evaporation. Thermal evaporation is a physical deposition technique. As per the name, the material to be deposited is brought in the vacuum phase by the virtue of thermal energy to the atoms of material in solid form. And then these atoms are transferred to a cooler substrate from the heated source. Evaporation is achieved by Joule's heating by applying low voltage and high current. The synthesis process needs to be carried out in a properly designed vacuum system. That is, under high vacuum environment, vacuum of the order of 10 to the power minus 6 torr created by rotary and diffusion pump, so as to avoid uncontrolled oxidation of source materials and final product as well as that of the components of the synthesis system. Mean free path of the particles also increases in vacuum systems, which is often desired as it should be greater than the dimensions chamber and source to substrate distance. Under such conditions, the transport of the material from the source to the substrate occurs by molecular beams. Sometimes reactive gases are used in certain cases of depositions. In that cases, it is useful first to evacuate the system to very low pressure so that the materials to be synthesized do not get contaminated by undesirable atoms, and then pressurize the system to desired value by introducing the high purity gases in the synthesis chamber. The illustrative layout of the thermal evaporation unit has been presented in the figure given on the next slide. The given figure shows the illustrative layout of the thermal evaporation unit, in which we can see the crystal oscillator for the thickness of the deposited film. Then there is copper coated samples. Then, for example, Here we are showing the gold material that is to be evaporated, which is kept in the tungsten molybdenum boat. You can see the electrodes, we can see the vacuum inlet, and we can see the LT supply. Heating of the material can be carried out through some suitable filament, crucible, boat, etc., which are collectively called as evaporation source or crucible, which is in intimate contact with the evaporant and is heated electrically. Evaporation sources are generally made of refractory materials such as tungsten, molybdenum, tantalum, and niobium because they have a low vapor pressure at the evaporation temperature and low reactivity with the evaporant. The thickness of the deposited thin film is monitored with the help of quartz crystal oscillator placed in the vicinity of the substrate. The final thin film produced by evaporation technique is in general non-stoichiometric because it is difficult to achieve conformal coverage during evaporation. It is very likely that the compound used for evaporation dissociates before getting evaporated. Therefore, evaporation technique for the thin film deposition has been suppressed in many instances or has been replaced in many instances by sputtering and CVD methods. A Hindevac thermal evaporation system is shown in the figure given below. It consists of a 4-inch oil-based diffusion pump backed by a rotary pump to attain high vacuum of the order of 4 into 10 raised to minus 6 torr. The vacuum system equipped with quartz crystal base thickness monitor to control the in situ thickness of the deposited thin film. So let us study what is sputtering. Sputtering is a high energy fabrication method to produce thin films, especially for obtaining stoichiometric thin films, that is without changing the composition of the original material from target material. Target material may be some metal, alloy, ceramic, or any composite material. Sputtering is also effective in producing non-porous compact films. Sputtering is an efficient technique to deposit multilayer films for mirrors or magnetic films for spintronic applications. Atoms from a solid target source are ejected or sputtered via a process of momentum exchange inside the plasma by the action of high energy ions, usually originating from some inert gas ambient like argon. The ejected particles are then deposited or condensed on the surface of the substrate to produce a thin film. So sputtering this is how a vacuum coating techniques. Plasma, the word which is taken from the Greek word called plasane, meaning to mold or to spread. So plasma is an ionized gas that is considered to be a distinct phase of matter. Plasma is an ionized state of matter containing ions, electrons, and neutral species. Plasma is electrically conductive and is strongly influenced by electric and magnetic fields. Plasma is used to derive ionization, creating a large number of ions and free electrons. Plasma is generated by applying direct current or alternating current voltages, and a bias voltage is applied to the target to promote acceleration of ions. Inert gas ions like argon are made incident on the target at a very high energy. Depending on the energy of ions and the ratio of ion mass to that of target atoms, the ion-target interaction can be a complex phenomena. That is, the kinetic energy of the impinging particle largely dictates what event would take place. Then the figure given here shows a schematic picture of various possibilities. For the deposition of materials, one is interested in the sputtering yield, which is the number of ejected species per incident ion and increases with the energy and mass of the bombarding ions. Sputter yield for different elements with same incident ion having same energy varies in general. Therefore, for a target consisting of two or more than two different elements, one having more sputter yield is incorporated in more amount than the others. However, high sputter yield elements get depleted fast and the other elements make higher contribution. Thus, the stoichiometry is achieved in the deposited thin film. So the figure given here shows the schematic picture of the possibilities of the phenomena occurring inside the sputtering chamber. Sputtering deposition can be carried out using direct current, that is DC, alternating current or AC, or radio frequency, that is RF, or magnetron sputtering. In general, the sputter yield is greatest with the following set of conditions. Number 1, high atomic weight process gas. Number 2, low atomic weight cathode material. And number 3, low concentration of reactive gas species in the vessel. Argon is the most commonly employed process gas for sputter deposition process, as it has high sputter yield for most metals. It is chemically inert and non-toxic and is relatively inexpensive compared with the other noble gases such as krypton and xenon. On the other hand, oxygen gas is known to react chemically with metals, forming metal oxides easily. Thus, argon and oxygen gases are used in deposition of metals and metal oxide thin films respectively. The figure given here shows the electron beam evaporation setup or the schematic, in which we can see a substrate holder, then the evaporated source material, a molybdenum or graphite crucibles containing the source material. We can see an electron beam. Then there are magnets for focusing electron beam. Electron beam source is there. There is a vacuum system to create the vacuum inside the chamber. And there is an inlet for the cooling of the source materials using water cooling. And in the end, there is E-beam power supply. Electron beam evaporation. Electron beam evaporation is an evaporation technique in which an accelerated beam of electrons from cathode is made to hit the target at anode, leading to vaporization of target material. These vapors get condensed on the surface of substrate to form a thin film of target material. Tungsten filament is used as the source of electrons. This filament is heated by passing a high current through it, which leads to thermionic emission of electrons. These electrons are focused to form a beam by applying magnetic field. The beam then strikes the source material, which is placed in molybdenum or graphite crucible. The beam is swept across the surface of the source material to uniformly heat all of the material. The material is then evaporated and condenses over the substrate surface. E-beam evaporation is similar to thermal evaporation but has some advantages over thermal evaporation. For instance, In an E-beam, a large amount of energy is supplied to the target material. Thus, materials having high melting temperature can also be evaporated using this technique. Also, E-beam evaporation process involves heating of only the source material. So, very low degree of contamination from the crucible occurs as compared to that in thermal evaporation. The next technique for the vacuum deposition of thin film or the vacuum thin film deposit unit is the molecular beam epitaxy or the MBE technique. MBE is a technique to deposit monocrystalline film. Epitaxy means the growth of crystalline layers on crystalline substrate. So MBE involves the epitaxial growth where the interaction of one or more molecular or atomic beams that occur on the surface of a heated crystalline substrate. MBE is performed in ultra-high vacuum, that is of the order of 10 to the power minus 11 torr. It is a very slow growth process, so very precisely control over the major compositional variations and impurity incorporation can be achieved using this technique. Now there are two types of epitaxy. One is the homoepitaxy, meaning substrate and material are of same composition and they are used to fabricate layers with different doping levels. The second type of epitaxy is heteroepitaxy, in which substrate and material are of different kinds like gallium and arsenide. This is used to fabricate integrated crystalline layers of different materials. In molecular beam epitaxy process or the MBE process, the term beam means the evaporated atoms do not interact with each other or the chamber of walls or with other vacuum chamber gases until they reach the wafer or the substrate. Epitaxial growth takes place due to interaction of molecular or atomic beams on the surface of a heated crystalline substrate. The vacuum system consists of a stainless steel chamber. The pumping system usually consists of ion pump, rotary pump, turbomolecular pump and cryogenic pump for the pumping of specific gas species. Ultra-high vacuum is used to obtain sufficiently clear epilayer. MBE generally has application in manufacturing of heterojunction bipolar transistors used in satellite communication, electronic and optoelectronic devices like LED, or in the construction of quantum wells, quantum dots, quantum wires, and low temperature superconductors. Plasma enhanced chemical vapor deposition or PECVD. As the name suggests, it is a chemical deposition technique. In this process, thin films of various materials can be deposited on substrates at lower temperature than that of standard chemical vapor deposition. In PECVD processes, deposition is achieved by introducing reactant gases between parallel electrodes, that is a ground electrode and an RF energized electrode. The capacitive coupling between the electrodes excites the reactant gases into plasma, which induces a chemical reaction and results in the reaction product being deposited on the substrate. The substrate, which is placed on the grounded electrode, is typically heated to 250 degrees Celsius to 350 degrees Celsius depending on the specific film requirements. In comparison, CVD technique requires 600 to 800 degrees Celsius. The lower deposition temperatures are critical in many applications where CVD temperatures could damage the devices being fabricated. The figure given here shows the schematic or the layout of the PECVD deposition system, in which we can see the gas inlet, top electrode, then there is a substrate holder, and there are pumps to create the vacuum. Typically, PECVD is used to deposit silicon nitride, silicon dioxide, silicon oxynitride, silicon carbide, and amorphous silicon. Silane, that is the silicon source gas, is combined with an oxygen source gas to form silicon dioxide, or a nitrogen gas source to produce silicon nitride. Silicon dioxide and silicon nitride are dielectric or insulating materials commonly used in the fabrication of electronic devices to isolate multiple conductive layers, capacitors, and for surface passivation. These films are also used for encapsulation to protect devices from corrosion by atmospheric elements such as moisture and oxygen. So students, let us summarize what we have learned in this module. In this module, we have learnt about different techniques which incorporate high vacuum in order to deposit thin films for numerous applications. Each of these techniques has its own advantages and disadvantages. We learnt in detail about these techniques one by one and saw their advantages and disadvantages. For example, thermal evaporation is simple and cheap, but there is considerable amount of waste of source material during the process. While in electron beam evaporation, multilayer deposition is possible, but it is very difficult to control the deposition rate. Now, PLD has the advantage that it maintains the stoichiometry of the target material, thereby making it the best suited technique to deposit complex materials on the substrate in the same chemical composition as they are in target material. But the only major disadvantage it has is that the uniform deposition occurs only in a very small area, that is approximately around 1 centimeter square. So based on their pros and cons, different deposition techniques are used to fabricate thin films of various materials towards the various applications. Thank you.